Hi, I'm Brandon Graysley. I'm a high school math teacher. Let's look at how to solve linear systems by substitution. That is, if we have a couple of equations for lines, let's find out where those lines intersect. This can happen in three different ways. We could have a line like this and another line that is not parallel to it that crosses it somewhere. We could also have two parallel lines that do not cross because they are always the same distance apart. Or we could have a line like this and then another line that happens to be overlapping it and is exactly the same line, and so therefore they're kind of stacked up and they intersect everywhere. If you pick any point on one line, it's also on the other line. So any of those three things can happen. So let's start by looking at a few examples. Suppose we have a line like this one, y equals 2x minus 1, and this is in slope y-intercept form. And maybe we have another line like this, y equals negative 3x plus 5. So let's call this line A and line B. And we notice that the slopes are different, and so they will have an intersection point, like this example up here. And this is what we call the system, and it's a linear system because these are both lines, and there aren't any other things. Now, if you were to graph this, you could find that intersection point, except it's not, these aren't going to be whole numbers or integers. The intersection point will have fractions in it, and that's pretty hard to see when you're trying to do this graphically. So we're going to do this algebraically instead. So here's how this works. If we can find some intersection point, let's call it x1, y1. The little subscript means it's a specific point. And that's the label we're going to use for now. So if that point is an intersection point, so if we can find something like that, so that means it's a point on both lines at the same time. So if it is a point on one line and it's a point on the other line. If it is an intersection point, then we know two things. First of all, it's on the first line, which means y1 is equal to 2x1 minus 1. Another way to think about that, if I substitute x1 in for x, whatever that point's number is, then when I evaluate it, I will get this other number, y1. And that will also be true for the second line, for line B. Now these look really similar to these ones up here. The difference is that this is now a number. This isn't a line anymore. I've substituted a point in. This is a number, and this must be the same number. See the equal sign? Similarly over here, this is now a number. It's been evaluated at a spot. It is equal to y1. Now notice here, y1 and y1. Those are the same thing. That's the same number. Maybe it's like 17, something like that. But the equal sign here shows us that that must also be the same number, and that must also be the same number. So if y1 was something like the number 17, this is 17, this is 17, this is 17, this is 17. And in particular, notice that those two things must be, 17. They're the same. Because they're equal then, I can write that as an equation. I can set them equal to one another. 2x1 minus 1 is equal to negative 3x1 plus 5. Because they're the same number here and here, I can write it as an equation. Now we solve this, and I'll get 2x1 plus 3x1 equals 5 plus 1. Over here, 5x1 over this side equals 6. Dividing both sides by 5, I'll get x1 equals 6/5. Now see, that's a fraction. That would have been tricky to get graphing, unless maybe you had a graph of unusual size. Now, that is not a point, though. That's just part of our intersection point. We need to find the y1 part, which is pretty easy because we have two different equations we can use to find that. Let's use this first one up here. y1 is equal to 2 times x1, which we now know is 6/5, minus 1. So y1 is equal to, let's call that 12/5. Instead of writing minus 1 again, I'm going to write that as a number of fifths, 5/5. And therefore we know that y1 must be 7/5. So in conclusion here, the intersection point, and there is just one, is the x part is 6/5 and the y part is 7/5. So that is the solution to this system. That is the point that is on both of these lines, and it'll be the only one because we found one, exactly one. Let me just show you right here. If we have an intersection point, then the x value must be 6/5 and the y value must be 7/5. There aren't any other options for us. Okay, well, what happens if, let me back up one more time. These equations were both in slope y-intercept form, so we were able to see something that must be the same and set them equal to one another. But that's not always true. What happens if we're given something like this? There's one equation, and here's another equation, so we'll call that one A. Okay, so one of those is in standard form, and the other is in slope y-intercept form. Let's do the same thing. If we have an intersection point, let's call it x1, y1. If we have an intersection point, then we know that each equation is true at that point. So 3x1 plus 2y1 minus 5 equals 0. That is, x1, y1 satisfies the equation. And we also know that y1 is negative 2x1 plus 1. Well, let me grab my red pen here again. There's a y1, which before we had a couple of those, and there's another one over here, but it's not isolated. It is isolated on this side, so whatever that number y1 is, this is the same number. And so this is where the name of this method comes from. Because this red box over here is equal to y1, I can replace that y1 right there with the same expression, with whatever this number is. It's the same as this number, it's the same as this number. So we're going to do that substitution, and it'll have a really nice effect for us. No, I spelled that wrong. Substitution. Close enough. So here it is. I'm going to replace y1 in this equation with a different expression for y1. It's like this is a word and this is a phrase that means the same thing. So right there, that's the substitution. I've replaced y1 with an expression for y1. And now I'm going to simplify and solve this equation. 3x1 plus distributive property, 2 times, oops, I should have not used a plus sign there. 2 times negative 2x1 is negative 4x1, so subtracting 4x1, plus 2 minus 5 equals 0. Over here that's negative x1 minus 3 equals 0, or that's the same as x1 equals negative 3. Okay, so I've found the x1 value that is the only one that will satisfy both equations. And so now I can calculate y1. Same way I have an equation with y1 isolated. So I'll use it. And let's see, that'll be 6 plus 1. y1 equals 7. So then the intersection point is the x part and the y part. Okay, well, in that case we still had one equation that was in slope y-intercept form. What if that doesn't happen? What if we have two equations like this? Here's equation A, and here is equation B. Let's see, this one looks good. Alright, so two equations, both in standard form. Neither one of them has a variable isolated. So let's start off in the same way. If x1, y1 is an intersection point, then what must be true? Well, the first equation is satisfied by that point, so 2x1 minus 5y1 plus 1 equals 0. It is true at that point, and the other equation is true at that point. x1 minus 3y1 minus 7 equals 0. Okay, well, one option that we have for how to proceed, we could convert one of these equations into slope y-intercept form. And that'll always work. It's not super efficient in this case because look over here. See, this has an x term, x1 term here, this coefficient is 1. There's nothing over here, where if I were to try to isolate for y1, there's a coefficient of 3, and I would end up with some fractions. So instead, what I'm going to do over here is just isolate x1. So adding 3y1 plus 7 to each side, I get x1 equals 3y1 plus 7. And so now what I have, instead of substituting for y1, in this case I'm going to, just by chance, I'm happening to substitute that in for x1 because they are equal into this equation. So that's the substitution that I'm making in this case, just because it's convenient. It could just as easily have been a substitution for y1 if it was more convenient. And so, putting those together, oops, sorry, wrong color. There we go. 2 times x1, but instead of saying x1, I'm going to say 3y1 plus 7. That's the substitution. So there's the rewritten first equation, which has taken sort of a piece of the second equation and mixed it in there. And so let's see what we have. This is 6y1, this is plus 14, minus 5y1 plus 1 equals 0. Simplifying, on this side I get y1 plus 15 equals 0, or y1 equals negative 15. Now in this case we've got the second coordinate, the y part is finished. We'll substitute that back in to get the x part. I'll substitute it back into this equation right here that I made because I've already isolated x1. So x1 is 3y1, negative 15, plus 7. Let's continue and evaluate that. That's negative 45 plus 7. x1 equals negative, that'll be 38. So the intersection point is x value first and then the y value. Okay, so that is how this works when you have this situation. But it could also happen that you have parallel lines, either distinct parallel lines or equivalent parallel lines or identical ones. And so I'm going to start another video in a minute, part 2, showing you what happens for the substitution method when you have those situations. Thanks.